Hello everyone, welcome to our fifth tutorial. Today we will discuss a new topic called Diffie-Hellman. So Diffie-Hellman is a public-private key encryption technique. Let's start discussing it. So let's start with the first question. Okay, the question says, users A and B use the Diffie-Hellman key exchange technique with a common prime, Q equals 71. So there is something called common prime here. And a primitive root A equal 7. So there's another input called primitive root. Okay, if a user A has a private key XA equal 5, what is A's public key YA? So the first part of this question is asking how to generate, or it's asking us to generate the public key for user A, given that we have his private key and we have the common prime here and the primitive root here. So what is the equation that can help us to do so? It's as follows. So in order to get the private key YA, what we need to do is to do A, which is the primitive root, power XA, which is his private key, the user's private key, modulus the common prime, which is Q. So in our case here, what we will do will be as follows. A is equal to 7, so it's 7 power XA, which is 5 modulus 71, and this will be equal to 51. Okay, so let's go to the second part. If user B has a private key XB equal 12, what is B's public key? So it's just the same like the first part. We will do YB equal A X B modulus Q. So it's 7, which is the same primitive root, power XB, which is now 12, as 12 is the private key for B, modulus the same value, 71, which is our Q, that is the common prime. And this is equal to 4. So far so good. Okay, now with the third part, what is the shared secret key? So in order to get the secret key, we call it K. So in order to get K, what we need to do is as follows. We get B's public key, which is YB, power A's private key, which is XA. This is in case that A is the one who wants to generate the shared secret key. That's why we're using his private key. Okay? And we do this modulus Q, which is our common prime, which is this. So in order to get the common key here, it will be as follows. It will be 4, which is B's public key, power A's private key, which is 5, modulus 71, which is equal to 30. So in other words, since we used here A's private key in order to get this shared secret key, if B want to get the shared secret key, it has to do the following. It will put here instead of B's public key, it will put A's public key, and it will put here B's private key instead of A's private key here instead of this XA. It will be XB. Modulus the same Q, which is the common prime. And by the way, it will give the same exact value, which is equal to 30. Now with the second problem. So this problem illustrates the point that Diffie-Hellman protocol is not secure without the step where you take the modulus. In other words, the indiscrete log problem is not a hard problem. Okay, so we want to prove that the indiscrete log problem is not a hard problem. You are Eve and have captured Alice and Bob and imprisoned them. You overhear the following dialogue. Oh, Bob says, "Oh, let's not bother with the prime in the Diffie-Hellman protocol. It will make things easier." Alice said, "Okay, but we still need a base A, to raise things to. How about A equal 3? So that's the first given here, which is the base A equal 3. Bob, all right. Then my result is 27. Alice says, and mine is 243. What is Bob's secret key, XA, and Alice's secret key? Sorry, so this should be B, XB for Bob, and Alice's secret XA. And what is their secret combined key? So we want to get 3 keys here. We want to get Bob's private key, Alice's private key, and their shared secret key, K. So what do we have here? What we have here is A as the base, and we use this as the base of the log since they decided here to skip the part where they pick a prime number and do the modulus thing. So they're doing it using log instead. That's why we're trying to prove the indiscrete log problem that it is easy. So what we have here is Bob's public key, Alice's public key, and the base. And what we want to do is to get their private keys and their shared secret key. So as we said, since there is no modulus operation involved here, this problem simply reduces to getting the log directly. So if we want to get or compute Bob's private key, what we will do will be just as follows. We do log to the base A, which is their base here, and we put here Bob's public key. So this will be basically equal to log to the base 3, 27, which is equal to 3. And to do the same for Alice, we do XA equal log to the base A of YA. So this is Alice's public key, which is 243. So in order to solve it, we do the following. Log to the base 3 of 243, which is equal to 5. So far so good. So in order to get their shared secret key, we do as follows. So in order to get it, in order for Alice to generate the shared secret key, it will put Bob's public key power her private key. And in order for Bob to do the same, he will put Alice's public key power his private key. So in case it's Alice here, so it will be Bob's public key, which is 27 from here, power her private key, which is 5 here. And in case of Bob doing this, he will get her public key, which is 243, power his private key, which is 3. And both, surprisingly, not surprisingly actually, it's just math, will give us the same value, which is 143489007. And that's it. Okay, now with the third question. Alice and Bob wish to exchange a secret key using the Diffie-Hellman algorithm. They agree to use the prime number 71. So they use prime number 71 and a primitive root of 7. So they use Q equal 71 and A equal 7. Alice chooses the private key 6 while Bob chooses 12. So we know that Alice's private key is 6 and Bob's private key is 12. To their misfortune, Eve intercepts the public keys sent by Alice and Bob and execute a man-in-the-middle attack, or rather, woman-in-the-middle, to trick them into believing they have exchanged a key with each other, while in reality they would have exchanged 2 keys with Eve. Okay, so basically what we need to do here, we need to execute Eve's attack and obtain secret keys shared between Alice and Bob. We may assume that Eve chooses private keys 8 and 14, one for Alice and one for Bob. So basically, what we want to describe here or execute is an attack where Eve is communicating with both Alice and Bob without any of them knowing. So Alice thinks that she is communicating directly with Bob, and Bob thinks he is communicating directly with Alice, while in fact both of them are communicating with Eve. So let's just start by calculating the public keys of both Alice and Bob, since we have their private keys. Okay, so to start by calculating Alice's private key, public key, sorry, what we will do as follows. YA, which is Alice's public key, is equal to A, which is the value here, which is the primitive root, power Alice's private key, which is XA, modulus Q, which is the prime number. And this is equal to 7, which is here, A, power 6, because 6 is Alice's private key, modulus Q, which is 71. And this is equal to 2. In order to do the same for Bob, we'll do the following. YB is equal to A XB modulus Q, which is equal to 7 power 12, because 12 is his private key, modulus 71, which is equal to 4. Note that now we should calculate Eve's public key with Alice and Eve's public key with Bob, knowing that her private key with Alice, as we said here, is 8, and her private key with Bob is 14. So her private key with Alice is 8 and her private key with Bob is 14. So let's try to calculate let's call it Y Eve Alice, so EA, Eve for Alice, which should be equal to A power X E Alice, which is equal to 8, modulus Q. So this should be 7 power 8 modulus 71, which should be equal to 54. And remember, as we said, some of these modulus equations might be too large to be solved on the calculator at once. So if this one is too large for the calculator, for example, what we do here, we split it. So in our case here, we can split it to 7 power 3 modulus 71, 7 power 3 modulus 71, and 7 power 2 modulus 71. And we multiply the output, or the result of each of the three together. And the value, the output value, we will also use it and do another modulus 71 to get the final output, which should be equal to 54 in this case. So now we have the public key between Eve and Alice. We do the same for Eve and Bob. So it's Y, E, B, which is equal to A, X, E, B, modulus Q, which is equal to 7 power 14 in this case, modulus 71, which is equal to, actually, I'm sorry here, this one is equal to 27. This one is equal to 54. Okay. Now, what we want to do is that we want to use these public keys to calculate Eve's common key with Alice and her common key with Bob. So, in order to calculate her common key with Alice, let's call it KAC. What we do is as follows. We get Alice's public key, which is YA, power X AE modulus Q, which is 2 power 8 modulus 71, which should be equal to 43. And in order to do the same for Bob, let me clean something here. Okay, I will erase 0. So in order to do the same for Bob, we do K, let's say Bob and Eve, equal to the public key of Bob, since Eve is the one who is generating the key, power X Eve Bob, so it's EB, and O modulus Q, which is equal to 4 power 14 modulus 71, which is equal to 5. That's it for this question. Now that we have a shared key between Alice and Bob, between Alice and Eve, and Bob and Eve, technically Eve can easily communicate with both, and making them both believe that they are directly communicating with each other. Okay, now with the fourth question. So, in the man-in-the-middle attack on the Diffie-Hellman key exchange protocol, the adversary generates 2 public-private key pairs for the attack. Could the same attack be accomplished with one pair? Explain. So, the question here is asking if that it's possible for Eve to communicate with both parties, Alice and Bob, using the same key pair, public-private key pair. So the answer for this question is yes, it is possible, actually. So let's consider a scenario where it is possible. So consider that A and B want to share a secret key, like the question before here, okay, using Diffie-Hellman protocol, while Eve is the one attacking the man in the middle attacker. Okay, so basically Eve will have access to Q and A, since both values are always known within the authentication process or the key exchange process. So the first step Eve would do would be as follows. Eve would choose a private key, let's call it XE, and we'll use it to generate a public key for herself such that Eve's public key is equal to A, the value that she intercepted here, power her private key modulus Q, which is this value here. Remember that Q and A here are two values that she has got from the communication between Alice and Bob. Okay, so far so good. So now she has a public-private key pair that are created using the primitive root and the prime number Q and A. Now the next step would be the next step that she needs to do is to start a communication with Alice and Bob. So what would Alice do? Alice would choose a private key XA, then she would create her public key YA using AXA modulus Q, and then B would do the same, of course. So he would have XB and YB, which he will get using AXB modulus Q. Now comes the step where Eve can intercept and intervene within the communication and hack it. So in the fourth and last step, after Alice has generated her public-private key pair, Bob has generated his public-private key pair, and of course Eve had generated her public and private key pair, A will should or will send to B his public key YA, the one Alice should send her public key to B, which is her YA here. But in fact, at this step, Eve will intercept and send her YE. So basically here, instead of A sending to B YA, what will happen is here Eve will intercept and send YE. And the same on the other side, when B sends to A his public key, which is YB, what will happen is Eve will intercept here and send the same YE. So basically, B will receive YE and A will receive YE. So when both start creating their shared keys, basically A will generate a shared key between between her and Eve, and Bob will create a shared key between him and Eve. So basically, both parties, Alice and Bob, will communicate through Eve. That's it. Okay, now with the next question. So the next question here is not about Diffie-Hellman, it's about hash functions. So hash functions are mainly used to check message integrity. Any function won't provide integrity unless it has some requirements. So let's start by discussing what is integrity. So when integrity is satisfied, it means that the message being sent is received at the receiver party just as it was sent from the sender party. What does that mean? In other words, a hash is a mathematical function or equation that we apply on the whole data, and it should come up with an output value, a certain value, okay? So when I want to send something to another party, I get this file, I generate a hash for this file, and I send the file, then I send the hash. So the other party, when the other party receives the file, he should run the same hash function to generate a value, a hash value, and should compare this hash value to the one I sent him. So if the file is indeed sent correctly, both hash values, the one I computed and the one he computed, should be exactly the same. If there is any change that happened during the connection, either there is a man-in-the-middle attack, someone intervened, someone removed something from the message, someone modified anything, or even there is a network-related problem that dropped some parts of the message, the hash value at the other side will not be exact to my hash value. So let's read here some requirements that need to be there for any hash function. Okay, the first requirement here, that it can be applied to any sized message m. The first requirement for any hash function is that it needs to be applied to any message. There is no minimum length or maximum length that needs to be used for the message to be hashed. Okay. The next point here, that it produces fixed length output h. So this means that a hash function should always result, or should always output a hash with a fixed length. So if the message contains one letter or 1,000 letters, the hash output will have the same exact length. The third requirement here is that it should be easy to compute. We should be able to compute h such that h is the hash of the message for any message m. So computing the hash should not be computationally expensive. This is one of the requirements. The next and the fourth step here is that given a hash h, it is infeasible to find an x such that h of x, which is the hash of x, is equal to h. So basically, the fourth property here is called the one-way property. This means that for a hash function to be correct, for this hash function, if I give someone a hash h, it is infeasible to find a value or a message x such that the hash of x is equal to this hash. So if I have the hash value of a message, I can never generate the message from this hash. And I can also never be able to generate a message such that the hash of the message is exactly the same hash I have in my hand now. The fifth property here says that given x, it is infeasible to find y such that h of y is equal to h of x. So here in the fifth property, it says that if I have a message x, it should be infeasible to find the message y such that the hash of y and the hash of x are equal. And this is called the weak collision resistance. Okay. Now with the sixth property, the sixth property says that it should be infeasible to find any xy such that h of y is equal to h of x, which is called the strong collision resistance. So the sixth property basically says that we can never find any two messages, x and y, such that the two messages have the same hash. So it's a little bit tricky, the difference between 4, 5, and 6. So let's go through them again. The fourth one, which is the one-way property, just says that if I have an input or I have a given hash h, I should never be able to find a message such that the hash of the message is the hash that I have, which is h. So I can never find x such that hash of x is equal to my hash. So that's why it's called the one-way property. Whenever I generate a hash, I cannot revert the hash and get the message from it. The fifth property says that given x, it is infeasible to find y such that hash of y is equal to hash of x. So if I have a message x, I should never be able to find another message y such that both messages have the same exact hash value. So the given here is x. In the fourth one, the given was the hash. It's mainly about the given and what I can generate from the given here. So remember this when you are trying to understand this part. Now with the sixth property, where it says that it is infeasible to find any x, y such that h of x is equal to h of y, which is the strong collision resistance. So this one basically says that we should never be able to find any message x, any two messages x and y, such that both of them have the same exact hash. So a hash function should be able to fulfill all these requirements. Okay, let's start solving some questions about hash functions. Let's start with the first question here. So here the question says, using an encryption algorithm to construct a one-way hash function, consider using RSA with a known key. Then process a message consisting of a sequence of blocks as follows. Encrypt the first block, XOR the result with the second block, and encrypt again, and so on. Show that this scheme is not secure by solving the following problem. Given a two-block message, B1, B2, and its hash. So basically, the equation is explained better here in this illustration. In this equation here, this is our encryption algorithm. So basically, here, the RSA hash algorithm of the two blocks B1, B2 can be done as follows. We get the RSA of B1 and we XOR it with B2, and then we RSA the output. Okay, so here the question says, given an arbitrary block C1, choose C2 so that the RSA hash or RSAH C1 C2 is equal to RSAH B1 B2. So the question here is asking us to find a collision to prove that this hash function is not correct. Thus, this means that we need to prove that the hash function does not satisfy the weak collision resistance. Remember? Pardon me. Remember, the weak collision resistance means that we should, given an x, a message x, it should be infeasible to find a message y such that they have the same hash. Okay? So, let's start solving this problem. So, our goal here is to find C2. Okay, to find the C2 such that the RSA hash of C1, C2 here is exactly equal to the RSA hash of B1, B2. This is our goal. We want to find a collision. Okay. So, if we are to use the same equation for RSA hash C1, C2, the equation for encryption should be as follows. RSA hash C1, C2 should be equal to, we should use the same equation here, it should be RSA of B1 XORed with B2. Okay, and let's try to equate this with the RSA hash of B1, B2 in order to try to get a value for C, or equation in order to get C2. Okay, pardon me, this is not B1, B2, this is C1, C2. Okay, just the same concept, I just copied it. Okay, so in order to equate this to achieve this collision here, we want to equate the equation for RSAH C1, C2 and the equation of RSAH B1, B2. The equation for RSAH C1, C2 is this one here, So we can type RSA of RSA C1 XORed with C2, and this should be equal to RSA of RSA of B1 XORed with B2. Now let's try to solve this, and we know that we should have C1 and B1 and B2 as inputs, and we want to get C2 such that this equation is satisfied. So the first thing that we can do here, since both have this RSA block out there, we can cross it at both sides, and nothing should be wrong so far. The equation should still hold. Okay, so now after we cross it, we have the following. We have RSA of C1 XORed with C2 equal to RSA of B1 XORed with B2. Okay, what do you think we can do here in order to get C2? In fact, the answer here is extremely simple. Remember, when we have an XOR, in order to, let's say, in order to send this part to the other side of the equation, what we need to do is just XOR it on the other side. So the reverse of XOR is another XOR. So here, actually, we can just reformulate the equation as follows. C2 equal RSA of B1 XORed with B2 XORed with RSA C1. See what I did here? So using this, we can get C2. This can be a representation, a valid representation for C2. So if we want to use this C2 representation in the bigger equation, we can do as follows. We can represent RSA hash of C1 C2 as follows. It says RSA of C1, which is the arbitrary block that we should have, XORed with C2, and now this is C2. So we put this C2 here. Okay, so far so good. So if we do this, what do you think it should be? Let's rewrite it in a better way so that we can see. I will just erase all. So it should be as follows. It should be RSA H C1 C2 equal to RSA of C1 XORed with RSA of C1. Remember, this part is from the C1 from the C2 representation we wrote on the other line. Here, this should be XORed with RSA of B1 XORed with B2. Okay, so a fact that we should know here, that an X XORed with X is equal to 0. Okay, and X XORed with 0 is equal to X. Okay, so if we have two things here that are XORed with each other, we can cross them out basically. Let's see what we have here that can satisfy this. So basically here we have RSA C1, RSA C1. So this O can be just 0. And 0 XORed with something is something. correct. So basically, what we can do here, when simplifying the problem, we can make it as follows. RSA H of C1, C2 should be equal to RSA of B1 XORed with B2, which is in fact the same as RSA H B1 B2. So we are able to reach the same hash from RSA H C1 C2. This is the proof for it. Okay, you can also read it in the practice assignment if you did not get it correctly here, and then come back and watch this part of the video. And of course, if you did not understand my illustration for this solution here, you can ask me in the interactive sessions. Okay, now with the second question in the hash functions part. Okay, the question says A and B want to verify that they possess a common key K using a public one-way function H. The verification process works as follows. A sends hash of K to B. B verifies that the received value is correct. And B sends back H, which is hash of K, to A. And finally, A verifies that the received value is correct. Given the verification protocol, answer the following questions. Why not have A send hash of K to B and then have B send H of K to A? So here the question is asking, why do we have here A send the hash of K to B in the first step and then receive in the third step the hash of K? Why not the reverse? So basically the answer is simple to this part. So if A sends H of K to B, then actually anyone can intercept this message and play the role of B. The reason behind this is that the hash function used is a public hash function. So anyone has the hash function that A or B is using. So if anyone has H of K, he can easily get the hash function and apply it again on the on the hash of K and have the H of K. But if we are to do the reverse of this, if we are to send the hash of K, if the intruder or the one who intercepts the message does not have K, he can never be able to get H of K. So let's go to the second part, double I. What keeps C from intercepting A's message, A's transmission of H of K, and then sending H of K back to A? So as I just said, if I have H of K, I can never go back and get H of K from it. What B does in order to get H of K is that B has the K, which is the message K or the key K itself, and it hashes it using the same function in order to get H of K and send this to A. But B should never be able to, or anyone should never be able to get H of K from H of K. This will violate the rule of the hash function. Okay, now with the next question. So there are some security requirements that we should read here before answering the question. Okay. So for this problem, assume that Alice wants to send a single message M to Bob. To do so, Alice and Bob can potentially use a number of different approaches and cryptographic technologies. which we will describe using the following terminology. M for plain text, SK for symmetric key. AES of SK is symmetric key encryption using CBC mode with the key SK, which is the symmetric key SK. SHA-256, which is SH-856 hash function. AES EMAC, which is a keyed MAC function with symmetric key SK. KA is Alice's public key. KA power -1 or KA inverse is Alice's corresponding private key. KB is Bob's public key, and KB inverse is Bob's corresponding private key. EK is public key encryption with the key K, and sign K inverse is digital signature using the private key. You can assume that the public keys have been securely distributed so that Alice and Bob know their correct values. Symmetric keys have not been exchanged. Consider the following properties that Alice and Bob might desire their communication to have: confidentiality, integrity, and non-repudiation. Okay, so let's give a quick reminder about confidentiality, integrity, and non-repudiation. So confidentiality here is satisfied when we are sure that no one is able to read the message but Alice and Bob. So no one should be able to intercept and read the message. If this happens, then if no one is able to read the message and we are sure that it is confidential, then we are able to apply the confidentiality property. Integrity means that the message should be received at the receiver side just as exactly like the message from the sender side, just as I explained at the very first part of the tutorial. Non-repudiation is a property that basically means that if we satisfy this property, we are sure that this message is not replayed by anyone else. So we are sure that the sender of the message is truly the correct one, and this message is not replayed by an attacker or an intruder. For each of the following possible communication approaches, mention and explain why which of these properties will not hold in the presence of a malware or a man-in-the-middle attack. Mention none if none of the properties hold. If an approach failed entirely, will not result in Bob being able to read a given message M, mention broken. Note that this sign here denotes concatenation. Okay, let's start with the first question here. So here it says Alice generates a new symmetric key SK and sends it to Bob. Okay, so here this is the symmetric key SK, and as you can see, it's encrypted with Alice's public key. Remember, if something is encrypted with my public key, it can only be decrypted with my private key. And if something is encrypted using my private key, it can only be decrypted using my public key. Okay, so it works both ways. And also a reminder, I never share my private key. I only share my public key. So no one can ever have my private key. People only have my private key. So here, when Alice sends the symmetric key encrypted with using her public key, this means that Bob should have her private key in order to decrypt the message. So this message cannot be decrypted unless her private key is used. So actually in this case, Bob will never be able to retrieve the symmetric key here. So in fact, he will never be able to decrypt the message. So this way is broken. Okay. Now the second question. Alice sends to Bob the following. She sends the message M encrypted with Bob's public key. And concatenated with this is the message M, the same message, the hash of the message M, basically. This is a hash SHA-256 of the message M, and this hash is encrypted using Alice's digital signature using her private key. So basically, the first part, that is the message with the encryption of with the message encrypted using Bob's public key, it means that only Bob will be able to decrypt this message. So this actually satisfies confidentiality. Okay. The second part, which is the digital signature of the hash, this part actually satisfies integrity due to the presence of the hash here of the message. So actually we satisfy also after we satisfy confidentiality, we also satisfy here integrity, since Bob will, when Bob receives this part and decrypt it using Alice's public key, since it's encrypted using her private key, he will recompute the hash for the message he decrypted on this site using the SHA-256 algorithm or function, and he should get the same exact hash. And if he did not, he will know that the message is not correct, and this is exactly integrity. The last thing that is satisfied here is the non-repudiation, only because we have this digital signature here. So we are sure that Alice is the sender, and we ensured non-repudiation when the message is encrypted using digital signature. So we have non-repudiation. Now with the third question here. Alice and Bob privately exchange a symmetric key, SK, in advance. Alice later uses this key to send to Bob the following. She sends the message M encrypted with AES using the symmetric key, concatenated with AES EMAC using the symmetric key of a hash SHA-256 of the message. Okay, so what does this satisfy? First of all, we are sure that this is not broken, since Bob will be able to retrieve the message here using the key SK that they exchanged earlier. So it is not broken. This part ensures confidentiality. So here we have actually confidentiality due to the AES encryption part, and we have integrity due to this MAC hash part. So basically, we satisfy both confidentiality and integrity, but we do not satisfy non-repudiation, simply because there is no signature that ensures that Alice here is the sender. Now, with the fourth question here, in the security requirements part. Okay. So Alice generates a new symmetric key, SK, and sends to Bob the following. She sends the symmetric key, SK, encrypted with Bob's public key. So Bob should be the only person who is able to decrypt this symmetric key. And she sends the symmetric key, the hash of the symmetric key, signed with her private key. And then finally, the message encrypted with this symmetric key. So this part here, which ensures that Bob is the only one who is able to decrypt this part. So he's the only one who is able to decrypt the symmetric key, and this message here encrypted with AES. These both satisfy confidentiality. Okay. Actually, the second part that is actually satisfied here is non-repudiation, since the message is signed. The hash here is the non-repudiation because the symmetric key is signed with Alice's digital signature. So this ensures that this ensures non-repudiation. The last thing, which is integrity. As you can see here, the hash function is applied on the key, not the message. So we cannot ensure that the message is transmitted correctly. So here, integrity is actually not guaranteed. So no integrity. Now with the fifth question. Okay. Alice generates a new symmetric key, SK, and sends to Bob the following. She sends the symmetric key encrypted with her public key, along with the symmetric key again encrypted with Bob's public key, and finally the message encrypted with this symmetric key, SK. So let's see what it satisfies here. So actually this scheme satisfies this will satisfy confidentiality, even though Bob will not be able to retrieve this part, so he will not be able to retrieve the symmetric key from this part, but he will be able to retrieve it from this part. Another problem here that he cannot be sure that she is the sender, since he is not able to decrypt. Also that Alice is the sender, since he is not able to decrypt this part. So there is no non-repudiation. And finally, there is no integrity because there is no hash. Okay. Now with the sixth question here. Alice sends to Bob the following. The message M encrypted with her public key, concatenated with the hash of the message, signed with her digital signature. So basically there is a huge problem here, which is the message here. The message is encrypted with her public key, meaning that it can only be decrypted with her private key. So this is broken, since Bob will never be able to decrypt the message. Now with the seventh and the last question for this tutorial. Alice generates a new symmetric key, SK, and sends to Bob the following. She sends the symmetric key, SK, encrypted with her public key, along with the symmetric key encrypted with his public key, with Bob's public key, along with the symmetric key encrypted with her private key, which is the digital signature. Okay, and finally concatenated with the message encrypted with AES algorithm with the symmetric key SK. So here, just look precisely, we have a huge problem. Actually, this one here does not satisfy any of the functionalities. Not integrity, not basically it can provide integrity. No, it does not provide integrity. So basically, it does not provide anything, and most of all, confidentiality, because of a huge problem. Remember, the signature, Alice's signature, is encrypted using her private key, which she only can have. But this means that it can be decrypted using her public key, which anyone can have. So if anyone decrypt this signature here, he can have the symmetric key SK. So anyone basically can decrypt the AES encryption here simply, without needing anything but decrypting the signature here using her public key. That's it. Thank you so much. See you next tutorial.